This is a summary sheet of values and calculations that you need to know. The right atrium has a mean of 5. Of course, this is millimeters of mercury. The right ventricle has a systolic of 25, a diastolic of 0, and a EDP of 5. The pulmonary artery has a systolic of 25, a diastolic of 10. The left atrium has a mean of 10. The left ventricle has a systolic of 120, a diastolic of 0, and an EDP of 10. The aorta has a systolic of 120, a diastolic of 80. And again, these are all millimeters of mercury. Okay, now aortic valve area. So remember that the aortic valve is a three-dimensional circle, basically. And so all that means is that it is 2.5 centimeters high and 2.5 centimeters across. So that's what's meant by the aortic valve area. So the normal aortic valve is 2.5 to 3.5 centimeters. The mitral valve is 4 to 6 centimeters squared. Normal O2 consumption for the body is 175 to 250 milliliters of oxygen per minute. The normal end diastolic volume in that left or right ventricle is 50 to 90 milliliters. The end systolic volume in those ventricles is 10 to 30 milliliters. So the normal stroke volume, so that's the amount of blood per stroke, is 40 to 60 milliliters. The ejection fraction is the percent of blood ejected out of the ventricles per beat. And so 100% of the blood is not ejected out of the ventricles. The max, it would be 80%. Your cardiac output is how much blood per minute. So that normal is 4 to 8 liters per minute. Then I have listed the pulmonary artery saturation. Your normal is going to be less than 75%, and your normal aortic O2 saturation is going to be above 95%. Okay, then we have the calculations. Stroke volume is end diastolic volume minus end systolic volume. EF, your ejection fraction, is stroke volume divided by end diastolic volume. Cardiac output, the angiographic method, is stroke volume times heart rate. Your oxygen content. Your oxygen content, first of all, you have to have the oxygen saturation for each blood vessel or chamber of the heart. Multiply that by your hemoglobin times the 1.36, which is the constant, and then times the 10 to get it in the correct units. Your normal oxygen, your oxygen consumption calculation is 125 times the BSA, which is body surface area. So again, these up here are your normal values, and then here below are the calculations to get the values. So for example, your stroke volume, when you do a calculation, this is what you would expect to be normal, is 40 to 60 when you do this calculation. Of course, the patients that we deal with don't usually have normal hearts and normal values, but this at least gives you in the ballpark as to, what a normal patient's values should be. Okay, so moving on down now to the cardiac output FIC formula. And while we're here, I want to just remind you that there are 3 ways to calculate cardiac output. The first way we've already talked about, which was the angiographic method. Second way is the FIC method. And then the third way is the thermodilution. Remember, that's the where you inject saline, which is at room temperature. It's injected into the heart, and then there's a thermistor located on the catheter that detects that temperature change once that is injected. But anyway, those are the three ways to calculate cardiac output. But the formula for the FIC formula, that's the one we need to memorize, is oxygen consumption, which again here is the formula for that, divided by arterial oxygen content minus venous oxygen content. Aortic valve area, the Gorlin method. Again, these normal values are listed above, and the formula is the cardiac output in milliliters divided by the heart rate times the SEP. The SEP is the systolic ejection period, basically the amount of time that the aorta is open during one cardiac cycle. And that is over the 44.3, which is the constant, times the square root of the mean pressure gradient. Remember, when we're talking about a stenotic aortic valve or a stenotic valve in general, there's going to be a pressure gradient. There's going to be a pressure difference on either side of the valve. And so that's what we're talking about here. And that value will be given to you. Then there is the mitral valve area, which is very similar. The only difference is that you are going to be using the DFP, which is the diastolic filling period. And so that's going to be the time, that's the amount of time that the mitral valve is open. And then the constant for it is 37.7. Also, you need to know that a valve area of less than 1 centimeter is considered a severe stenosis, which makes sense because if you look above at your normal values, a normal aortic is 2.5 to 3.5 centimeters, a normal mitral valve is 4 to 6. So it makes sense that less than 1 is considered severe. Okay, the last calculation is the shunt detection. So again, we're trying to decide how much and in which direction blood is shunting. Is it shunting from left to right, or is it shunting from right to left? And how much is it shunting? And so the shunt detection is made up of 3 steps, but I want to go ahead and scroll down and just show you that the end calculation is pulmonary CO over systemic CO. That ultimately is the calculation that gives us the ratio. But in order to get to this point, we have to do the other 2 steps. But these other 2 steps we've already learned in other calculations. So first is the first step for shunt detection is to calculate the oxygen content. And again, these are formulas we already know. You have to have the saturation first times the hemoglobin times the 1.36, which is the constant, times the 10 that gives you the correct units. Now the difference is when we are calculating a shunt and we're trying to find the mixed venous content, normally we could use the pulmonary artery, but when you're doing a shunt, you can't do that. You have to use 3 of the superior vena cava O2 saturations and 1 of the inferior vena cava saturation. Add those 4 together, divide it by 4. That gives you the average or a true mixed venous content. Now for your other types of calculations, a lot of times you can just use the pulmonary artery as your mixed venous, but in this instance you can't. You have to take 3 from the superior, 1 from the inferior, and get an average of those. Then once you have that number, then use that saturation times the hemoglobin times the 1.36 times the 10. So first step is to calculate oxygen content, so we know how to do that. Then after that is to calculate the cardiac output, which again we've already learned how to do that. And that is taking your oxygen consumption, putting that over pulmonary vein oxygen content minus pulmonary artery oxygen content. So that's pulmonary CO. And then systemic CO is basically the same, except you just take your AO oxygen content minus your mixed venous oxygen content. Okay, so again, ultimately those first 2 steps are just to get you to this point. You want to find out the pulmonary CO and the systemic CO, because in a normal heart, these 2 will be the same. So let's say that they are the same. And so let's say in a normal heart, the cardiac output is 5 over 5, so then that would equal 1. And so 1 is normal. But when you do the calculation, and if you have a value that is greater than 1, then you have a left to right shunt. And if you have a number that is less than 1, you have a right to left shunt. And also greater than 1.5 is the cutoff as to requires closure of that shunt. Also then, so that gives you the ratio. That tells you if it's left or right, it tells you if it's right to left, it tells you, how big it is, or it tells you, it gives you, again, a ratio to tell you if it's, if it needs closed or not. But also, too, then they want to know, well, how much volume is shunting. And so, again, that's easy enough. You just take the pulmonary cardiac output minus the systemic cardiac output, and then that will give you a number that'll tell you exactly how much blood is shunting per minute. Okay, so I think that's it. That gives you a summary sheet of the normal values and calculations. So it's a lot of information. It's a lot of important information. So be sure to spend time knowing this information.